Okay, so now we're ready to talk about fission and fusion. Fission and fusion. The process, as we mentioned earlier, both of these processes occur in nature. They're both really important for different things. And in terms of human technology, the only one, well, the one that's been utilized for making electrical power is fission. And this technology has been around for about 100 years. And it's been industrialized, since World War II. And basically, we'll use the real typical example is uranium. And as we were talking about uranium-235, so here's uranium-235. Hold on. And it decays into, well, let's talk about this first. So you have this unstable uranium nuclei, and it will decay on its own at some point. It's ready to pop. And not sure what the half-life is on this stuff, but it's quite long. And I wanted to mention this earlier. Some half-lives are in the order of milliseconds or nanoseconds. Some half-lives are in the order of billions of years. So the uranium is long-lived. So that means it's going to stick around for a while. And once you have it as radioactive waste, it's going to stick around. So anyway, this uranium, if you hit it with a single proton, so I'm just going to indicate this by a plus sign, meaning you hit it with a proton, it will split apart into two separate nuclei. And one of the smaller nuclei is going to be krypton 91. And so that's element number 36. And barium. Barium 142. And it is element number 56. And you also get 3 neutrons. So if you have a chunk of uranium and these neutrons come out and start hitting other uranium atoms, you get a chain reaction. And it turns out if enough of this stuff in one spot, the chain reaction will become what's called critical, and you end up with an explosion. And that's a nuclear explosion. So the first nuclear weapons were fission bombs, where the idea was to get a piece of uranium to become in this critical state, and the fission would all happen at the same time, and it would explode very violently. And so that's the type of bomb that was dropped. Those are the types of bombs that were dropped in World War II, were fission bombs. But on the peaceful side of things, fission is used in all of the nuclear power plants that we have. And so what you have basically is this, these rods of uranium that are in close proximity. And then you have rods of what's called a moderator, which can be lead, it can be other materials. I think you can even use water as a moderator. And as you move the moderator up and down, you control how fast the reaction's occurring. And so instead of becoming critical, it just gets hot. And there's safe ways of doing this, especially now. There's newer and newer nuclear technologies that are coming out where you can safely do fission where it cannot become critical. And also the waste is all contained in these glass-encased pellets, so they're not, basically it can't burn out, like meaning it can't melt down, and the waste can't get radioactive stuff into the environment. It just stays contained. And so it's kind of, maturing as a technology, but in the process we had a lot of really bad problems like Chernobyl and most recently the reactors in Japan. So anyway, how do we get energy out of this? Well, it's sitting there being very hot. And so it's the reactor core, which is this thing that I've drawn, is cooled by having water flow around it, and then that water goes through a heat exchanger. So let's draw the heat exchanger. Okay, anyway, I'm just a little crazy here. So the water's flowing through a heat exchanger, and then it exchanges heat with another coil of water, and this operates a steam turbine. And the steam turbine hooks up to a generator, and out comes your electrical power. Very simple, in theory. So basically you're converting heat into mechanical energy and mechanical energy into electrical energy. And so when you see those big cooling towers on nuclear power plants, what's coming out of those is just steam. And the steam has never been in contact with anything radioactive. There's usually at least one set of heat exchangers so that the water is being completely isolated from anything bad. So that's basically how a fission plant works. The other type of nuclear energy is fusion, and this is a much more elegant and clean solution. Basically, here's a typical fusion reaction. Here's a proton and a proton. And you put them together, and you get helium. And you can, there's all different ways of doing this. I'm not writing the exact reactions out. Maybe there's one listed in the book. Okay. Yeah, let's do the one that's listed in the book, just for specificity. So, if you take hydrogen 2, which is deuterium. Now, first of all, the most abundant hydrogen around is called protium. Protium is just a single proton, and it's got an electron around it. And this is the hydrogen that is found in most water. But a little bit of the water is deuterium, and a little bit is tritium. So we're going to take H2, which is deuterium, and we're going to add it to H3, which is tritium, and we're going to get helium. Okay, we also get a neutron. So this is a neutron over here. I drew it a little funny. Okay, so that's a single neutron. But in the process, we get a tremendous amount of energy in the form of the helium, that's a beta particle, remember? Beta? Or no, alpha, sorry. This is an alpha particle. And it's got a lot of energy, kinetic energy. And we can take that energy and do a lot of things with it. The neutron is also very energetic. We can use the neutrons to heat water and again make steam with that water. Also, the alpha particle is charged, so we can use it to generate electricity directly, which is kind of neat because we don't need the steam process in the middle. We can make electricity directly. And there are there's tons of different fusion reactions, and some of them you can make electricity directly from fusion without anything in between, which is great because it's very, very efficient, and there's no heat, there's no energy being lost as heat. So, anyway, so what's the downside? First of all, it's very hard to do these reactions. The reason is because the electrical repulsion between the hydrogen nuclei is so strong that it takes very, very high temperatures or energies to get this to happen. So when you start having to get stuff like gases really hot or plasmas really hot to do these reactions, you're putting so much energy into it that it leaks out of the container into the environment before the reaction happens, so you end up being under unity, meaning you put more energy in than you got out. So that's kind of one of the main, that is the main problem with fusion. Now, fusion has been done successfully, and it's been weaponized, obviously, as hydrogen bombs, which are incredibly powerful and truly a terrible weapon. So that's one type of fusion reaction that's been done, not a good one. But also there's a number of different fusion reactors that have been built that do indeed work. The only problem is they're under Unity. I think we've had a couple over Unity runs of the tokamak, but I'm not sure about that. But if it's not been over Unity, it's been close. The Lawrence Livermore Labs, which is a big government lab, has a laser fusion research center, which is promising. And there's also a number of promising fusion technologies, but they're always 20 years off. So basically, we haven't got there yet. But it probably will happen, and it'll probably happen, I would say, within the next 50 years, that we'll have fusion plants producing energy, and that will really be the end of energy problems, in the sense that we will no longer need any fossil fuels to run stuff, because the source for these fuels is just hydrogen, which is the most abundant, it's the most abundant element in the ocean. It's just water, and so you'll never run out. It uses so little that you will literally never run out. So anyway, that's our talk on nuclear energy. I'll make a few more comments in class, and we'll do our labs. Have a good week, and God bless you.